Good morning, one and all. Today we are going to discuss introduction to digital systems. That means digital system, as you know, it is how what is the difference between an analog signal? This is an analog signal, and here we have an A to D converter. That means A to D converter. A to D converter. Then this will be converted to a digital signal. This is digital signal. What is the difference between an analog signal and digital signal? Analog signal is continuous. That means it is represented by one straight line, and here we have, that means, and suppose that we are sampling in different discrete intervals, then that means at this point in time what is the value, at this point in time what is the value, at this point in time, this point in time. That means here you have a number of discrete levels for the digital signal. If you have only two levels, we call it as a binary signal. Binary signal. That means it has only two levels. For a binary signal, it is having two levels. And usually, when we are using this in a digital circuit, usually 0 is represented by 0 volt and 1 is represented by 5 volt. But this is the usual convention, and this can vary. That means here we have positive logic and negative logic. Positive logic and negative logic, I will tell you. In positive logic, 0 is represented by 0 voltage and 1 is represented by a higher voltage. A higher voltage compared to current voltage compared to 0 volt. That means in positive logic, 0 is represented by a lesser voltage compared to 1. 1 is having a higher voltage. If you are using negative logic, usually 1 is represented by 0 volt and 0 is represented by, say, 5 volt. That means here 1 is represented by a lesser voltage. 1 is represented by a lesser voltage and 0 is represented by a higher voltage. That is the positive logic and negative logic. In positive logic, the 0 representation, that means either 0 ampere or 0 voltage is used for 0, binary bit 0, and 1 is having a higher voltage or higher current compared to 0. And in negative logic, we are using vice versa. Okay. And when we are talking about the different kinds of functions, different types of functions, we have, say, when we are talking about different types of logic circuits can be broadly classified into combinational circuits, and sequential circuits. In the case of combinational circuit, suppose that this is a combinational circuit and this is having a number of inputs like this. These are inputs and these are outputs. That means out and combination. This is a combination circuit. That means circuit. combination circuit. This is a combination circuit, and here we have a number of inputs and we have a set of outputs, and this output depends only on the inputs. That means the output is dependent only on the inputs, and that kind of circuits are called combinational circuit. It doesn't have any memory. That means, but in the case of sequential circuit, suppose that this is a sequential circuit. Suppose that you have a set of inputs and you have a set of outputs, and these are outputs and these are inputs. Then the output depends on the current inputs as well as previous outputs. That means the previous value of this output and current input. That means it depends on the previous state of the sequential circuit. For example, suppose that you have a counter. Suppose that you are counting. That means after 1 you have to count 2. After 2 you have to count 3. That means every time you are adding 1. But it depends on the previous value of you have displayed. Suppose that here you are displaying say 1, 2, 3, 4, etc. That means here this is a sequential circuit to display an integer value on the screen. Display an integer value on the screen. Then suppose that the current value of in which the screen is displaying the value 1, and after that just display 2, after that just display 3. That means in a sequential fashion just to display. So in that case, actually what does the circuit do? It's actually incrementing the previous value. That means it is incrementing, and that output depends on the previous value also. But in the case of a combinational circuit, it is depending only on the current value of the input. It doesn't have any memory. That means in the case of combinational circuit, no memory, and here has memory. When we are comparing combinational circuits and sequential, almost all circuits are sequential. Very little use for combinational circuits, and almost all circuits are sequential circuits. Okay, and now we are going to study the basic elements of combinational circuits. What are the basic elements of combinational circuits? Basic elements of combinational circuit. Among the basic elements are gates. As you know, we have studied AND gate, OR gate, NOT gate, etc. And we are going to discuss some more gates. And here the first gate is an AND gate. And the representation of an AND gate is like this. And suppose that here A and B are the inputs, then F, the output will be A dot B, and is represented as AB. A dot B, and that is represented as AB. And the truth table for that is, suppose that you have A and B, and suppose that the function is A dot B. Here you have 0, 0, 0, 1, 1, 1, 0, 1, 1. And what is the output produced? Here f is equal to 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, and 1 into 1, 1. That means here for an AND gate there are two inputs A and B, and the output will be 1 if both A and B are ones. If both A and B are ones. Now the second gate is O, and that is represented by, this is an OR gate, A and B, and the output is F is equal to A or B. And the truth table, this is and now we are going to have the truth table for OR. This is A, B and F. This is OR gate. So A and B are 0 and 0, 0, 1, 1, 0, 1, 1. Then what is the value of 0 over 0, 0? 0 over 1 is 1, 1 over 0 is 1, 1 over 1 is 1. Here the meaning is the output will be 1 if either of A or B is 1. A or B, that means F is equal to A or B. That means the output, that means this A and B can take two values 0 and 1. So there are four different inputs, and depending on the inputs, if either of A or B is 1, then the output will be 1. And number 3, NOT. NOT is represented by, this is the NOT gate, and here you have a bubble here, here you have a bubble, and here you have only one input A, and that will be complemented. That means F is equal to A bar. That means that will be complemented, and the truth table for that is, here you have, this is the input A, and what is A complement? See, if 0 is input, A is the output, and if 1 is the input, then 0 is the output. So this is NOT. This is the truth table for NOT gate. This is the truth table for NOR gate. Now next one is NAND. NAND means not of AND. Not of AND means that is represented by, this is an AND gate, and after that this bubble is taken from here. That bubble means just to be complemented. That means the output of this is equivalent to, I am writing here, that means this is a AND gate, and here you are going to have a NOT operation, and this is, that means here you have A and B, here you get AB, and here you get AB bar. Okay, A dot B and AB, that is represented by this, and this is A and B, and the truth table for NAND is like this. This is NAND. A, B, AB, NAND B. That means A, B, this is F, A, NAND B. That means 0, 0, 0, 1, 1, 0, 1, 1. That means you have to multiply AB and then take the complement. So 0 into 0, 0 complemented 1. 0 into 1, 0, complement is 1. 1 into 0, 0, complement is 1. And 1 into 1, complement is 0. That means not of AND. That is NAND gate. And 5 is NOR. That means not of OR gate. Not of OR. That means after taking the OR operation, that means OR gate is represented by this. Okay. Here 12 inputs, then you are negating it, and this is equivalent to, first of all you are taking the OR, and then that output is fed to a NOT gate, and suppose that this is A and B, this is A plus B, and this is A plus B bar. A plus B bar. And the truth table for NAND is like this. Here, this is A, B, and A nor B. This is no. Okay. And if it is 0, 0, 0, 1, 1, 0, 1, 1, then what is 0 or 0? It is 0 and take the complement, that is 1. Here 0 or 1, it is 1 and take the complement, that is 0. 1 or 0 is 1 and take the complement, that is 0. 1 or 1 is 1 and take the complement, that is 0. So this is the truth table for NOR gate. NOR gate. Sixth one is exclusive or XOR. XOR means that is represented by, this is the XOR gate. Here we have two inputs A and B, and this is the output A XOR B. That means that is represented by, here you have A B and this is A XOR B. That means this is XOR. That means here 0 0 0 1 1 0 1 1. Here for these three, that means A or B, 0 or 0, 0 or 1, 1 or 0. That means here OR is same for three rows. That means 0 0 0 1 1 0. That means 0 0 it is 0, 0 or 1 is 1, 0 1 XOR 0, that is 0. Sorry, this is also 1 and 1 or 1 is 1 XOR 1 is 0. Okay, so the difference between OR gate and XOR gate is for 1 1 this the output is 0. That means if the inputs are same, if both the inputs are same, then that 0 will be the output, and if the inputs are different, then the output will be 1. Output will be 1. Okay. Now the seventh one is XNOR, which is indicated by, that means you are going to negate this. That means XNOR, and XNOR is represented. XNOR is the complement of XOR. Okay, this is A, B, this is XNOR, and this is the output 0 0 0 1 1 0 1 1. That means if like inputs are same, like inputs are there, then the output is 1, and if unlike inputs are there, then the output will be 0. Okay. With that, the basic elements of combinational circuits we have discussed.